Okay. By the way, have you guys noticed the prep quizzes, like what the bracket things, like what the letters mean? Okay. Yeah. Well, you haven't seen the AC ones. That was a postdoc from when I took it my year, Francis Super. Okay, wait, let me see the poll. Okay. So 75, how many do we have so far? 4 people. Okay, let's get a few more opinions. Oh, yeah, I'll show the question, sorry. Okay, oh wait, okay, couple seconds. Okay, majority say 3. Okay, would anyone like to explain why they think it's 3? Yeah, go ahead. What's your name? Sorry. Celia. Okay.
Well, I think the answer 3 would be because that means that a whole row or a whole column could be zeros. But I mean, in theory, if there are 3 zeros, then I don't think that necessarily means that it's half the number, but I think that that's the minimum that it can be, like with zeros.
Yes. Okay. So yes. So 3 is the common answer that you first think of, because you're like the whole row is zeros. Like it's not invertible. But if you have zeros in other places, like some random zeros, then it might necessarily not, like it might still be invertible. It's possible, right? Like if you had something like this, there's 3 zeros, but this is still invertible. So, but the question is, like, how many zeros do you need to guarantee no matter what you do, it has to be invertible? So if you think of the simplest matrix, we know the identity, right? The identity matrix is always invertible no matter what. Right there, there's already 1, 2, 3, 4, 5, 6 zeros. So the determinant, so this is invertible. But if you take out one of the ones and replace it with another 0, that automatically makes it not invertible. Because no matter what you do to take the determinant, you're always going to get 0. So the correct answer that Bryce was expecting was that you need 7 zeros for this specific case. Because no matter what, how you put the zeros, as long as you always have 7 zeros, no matter what, it's going to be invertible for this matrix. So you can actually generalize this so that in general, for an m by n matrix, what did we do to get 7? We did how many total terms are there, which is 9, minus like how many are on the diagonal. Then we just added 1, the extra 0. So in general, you need n squared minus n, which is the number of diagonals you have, plus 1 zeros. Any questions? Okay, let's move on then. All right, so on to new stuff. So let's go over linear transformations. So there's 4 main types of transformations, right? Rescaling, projecting, shearing, and rotating. So first, without even thinking about the types of transformations, you can think of a matrix as telling you some form of transformation. So if you just have the identity matrix, like 1, 0, and you have just a vector 2, 1, this matrix A will transform the vector 2, 1 to the same exact vector. How do we know that? Because we usually do A times this vector to get what the new vector will be. So this is the most basic matrix, the identity matrix, and it doesn't do any transformations, like it stays the same. But let's go on to rescaling. So if you have a matrix like this, generally, how do you find this matrix A? Well, we look at the standard basis. The standard basis is I, or the green one. So this is 0.10. And then your orange one, or J, is 0, 1. So say that we wanted to transform it to these two vectors instead. First, we look at the green one. So the green one, we went from 1, 0 to specifically 2, 0. 2, 0. Right, and then the orange one, we went from 0, 1 to 0, negative a half. Okay, so what does that mean for our A? It means that our A is now, well, this new I vector, we transformed it to 2, 0. So we can put it in the location where the 1, 0 originally was. So we put the 2, 0 there, and then the 0, 1 became a 0, negative a half. So we put that in the second column. And so this is the matrix A, which describes our transformation, this transformation. Any questions on rescaling? Okay, yeah.
I had a question about the order, like,
Mm-hmm.
that order.
Yes, because so in the original case, we have the identity matrix. So the 1, 0 vector is the first column. So we want whatever happens to 1, 0 to always be that first column. Okay, so let's do projections then. Okay, let's just do an example since I don't want to explain stuff. So write the linear transformation that sends the vertical to the line y equals 4x. Okay. Why not? Do you guys want to work in groups or like by yourselves? So we can like group you guys. Okay, just work on this question, I guess, then. Or if you already know the answer, you can let me know what you think. All right, does anyone have any ideas for what we should do as the first step? Yeah, what's your name?
No.
Noah, okay.
Well, you need to figure out how to transform the orange vector
Mhm.
to multiply it, get to 0, 4. So and that's just 4. And then for the green vector, you can get 0. So that's just
Yes, so the green one, so we're projecting to the vertical line y equals 4x. So here we see with the pink arrow, we want to project, as Noah said correctly, the 1, 0 vector all the way back to 0, 0. But what about this orange vector? So right now the orange vector is at 0, 1, and we want to move it over, meaning that it should still have the y value of 1. It just has a different x value now. So like we want to find what is this point right here. So we know that the red point is going to have a y value of 1. So we just need to figure out the x. So the x is 1/4. So the orange vector goes to 1/4, 1. And now that you know what happens to the green vector and the orange vector, you just write what is this matrix transformation. You write the green one, then the orange one. Any questions? Okay, so this was matrix projection horizontally. So we saw it going horizontally, the green, yes.
So you don't have to scale it?
No, so this is just like projecting to some line. So you're not really scaling it.
I see.
Yes. So this is projecting horizontally to some line. Similarly, there's also like another thing where you can project vertically onto the line. I won't do this, but it's in my notes and you can check it out. It's the same concept where you want to see the green vector. Projecting vertically means that you're keeping the x value instead and finding whatever new y value it is. And the same with the orange vector, projecting down vertically. Okay, let's move on to shearing then. Okay, so intuitively, let's just go over how would shearing work. So you've noticed a pattern that we keep saying, where does 1, 0 go? Where does 0, 1 go? And then you make your matrix. So it's always the same pattern. So for the green vector, we're sending 0, 1 to, wait, 0, 1, 0, sorry. 1, 0 to, if we're shearing. So shearing means that you're kind of like completely moving your axis a little bit. So rescaling, we extended the vectors or shrink the vectors. Projecting, we projected onto some line, but shearing is like you're shearing along some other line. And like kind of, if this purple is your first plane, we're moving the plane now to this purple plane. Okay, so the green vector, you see that it stays where it is, so it's 1, 0. What about the orange vector? The orange vector is 0, 1. But now where is this new point that the orange vector went to? Well, we need to figure out what that point is. So the y value, you notice that the y value is still 1. So we need to figure out what this point is if the y value is 1. Again, this line is this line. Oh, I wrote it here. Ax plus by equals 0. Ax plus by equals 0. If the y value is still 1, we have 1 like that, and then we solve for x. So this is just in general, for any line, 0, 1 will go to negative b over a, 1. In general, for any line. Thus, our matrix A will be 1, 0, and negative b over a, 1. Any questions on shearing? Yes, what's your name?
Zane.
Zane.
Why did only the J vector change? Why did the I vector just stay in the same spot?
Because so the x, okay, let me see, shearing along, so this version we're shearing along the x-axis and taking the y-axis to some line. So in this case, the x-axis, we're keeping it the same and we're just shearing the y-axis. So this is the first version. The second version is where you're shearing along the y-axis and taking the x-axis to the line. So in this second version, your y-axis would stay 0, 1, and then your x-axis would change. So shearing is like shearing one of the axes to move. Any other questions? Okay, last transformation is rotation. So rotation, you can look at like the proof for why it works. Cosine theta, sine theta, negative sine theta, and cosine theta. So let's do a quick example. Oh, let me copy that so you guys see it. Okay, write the linear transformation that rotates the plane 30 degrees counterclockwise. So this matrix A, this is the matrix that we always use doing a rotation. And specifically, it's always for if we're doing something counterclockwise. So in order to find out what is the linear transformation that rotates our plane 30 degrees, you just plug in 30 for your theta. So our A is going to be cosine 30, which is 30 is also pi over 6. Yes, sine of pi over 6, negative sine of pi over 6, cosine pi over 6, which will equal square root of 2, half, negative a half, and square root 3 over 2 again. So this is the matrix that describes the transformation where you rotate a plane 30 degrees counterclockwise. Now, if it had asked for clockwise, you just plug in negative 30 degrees instead. So that's the only difference. Any questions on rotation? Okay, and one last thing about transformations is that if you're asked to find a transformation and they give you like find the matrix that 1 rotate or rescales by 2, rotates by 30 degrees, etc. How you do it is that you first find the matrix for that first transformation, find the matrix for second transformation, but when you're multiplying, make sure you start on the right side and go down. So if there was a third transformation here, and we had a matrix, matrix C for that describes the third transformation, you shouldn't do A times B times C to get your like transformation. This is wrong. You should do, you start from the first one, which we said was A, then go to the left. So C, B, A. And you would multiply that out to get whatever matrix it is. Any questions on compositions? Yes. Mhm. Yes. Yes. So you should find the matrix corresponding to each thing and then actually multiply it out. Yes.
Unless otherwise like specified, we always assume that like what's being transformed is like having our identity, like our basis.
Yes, like to find like what it is, you go.
Yeah, like, if it says like find the transformation that like has a question for transformation.
Mhm.
Find the transformation that sends the vertical to the like y equals first. We're assuming the vertical is like 0.
Yes. Yep. Any other questions on this? Yes. Mhm. Reflecting across a line. Let me think. You could do it multiple ways. You could do a rotation. Wait. Reflection across the line. Since the vertical. I feel like that'd be what is this projection? But I'll have to double check on that. Any other questions? Okay, let's do change of bases then. I know this is probably the most confusing thing of this week, or that I felt like. Okay, so in general, the reason we've never heard of change of basis is because whenever we're given some vector, for example, vector 1, 2, like we just think, oh, it's a vector 1, 2 with our normal x-axis and normal y-axis. But what does 1, 2 really mean? 1, 2 is what we're writing in a standard basis, which I'll just call S. Our standard basis, I'll write in purple here. Our standard basis is always 1, 0, 0, 1. 1, 0 is the x-axis, 0, 1 is the y-axis. So what does 1, 0, 1, 2 really mean? What we're doing is we're doing 1 times the I vector plus 2 times the j vector. So in this sense, we're writing 1, 2 as a linear combination of the basis vectors in the standard basis, which we always just consider is the standard, like regular basis we use. Now, change of basis is that what if we don't have the standard basis? We have some new basis. So for example, if we had this basis 1, 2, and 1, 1, and we want to write 1, 2 in the basis of B, what do we do? So what we want to do, what did we do above with the standard basis? We wrote 1, 2 as a combination, meaning like you do a multiple of the first basis plus a multiple of the second basis. So we do the same exact thing. We write 1, 2 as some number times our first vector basis vector, plus some number times the second basis vector. Now, what are those numbers? Yeah, 1 and 0. So this is 1, this is 0. So 1, 2 written in the basis of B is actually 1, 0. We just take what this number is and what this number is, and we write that this vector in this weird basis turns out to be 1, 0. Does any questions on that? Okay, in this example, it was easy though, right? We could tell like, oh, 1 times 1, 2 is obviously 1, 2, right? But what if it gets harder? What is a way that we learned from last week for how we could solve what these numbers are? Any, yes, Noah?
I have a question about this.
Yeah.
So would this be like when they say like, oh, it's like an orthogonal orthonormal or orthonormal basis? Is that like is that a question they ask on bases? Or is that like something different? Like coordinate systems maybe? Or?
Yeah, so orthonormal basis is I think the length of each vector has to be 1 in order for it to be orthonormal. I think if I'm remembering correctly, or maybe I'm not remembering correctly. Let me search orthonormal. Oops. Yeah, it should be. If the basis is orthogonal and the basis vectors are all of unit length, then the basis is orthonormal. So in our example, the basis is not orthonormal because this length isn't 1. And this length also isn't 1. Yes. Okay, yes. So we want 1, 2 to equal some number times the orange plus some number times the 1. So if we make the first number 1, then we already have what our goal was, 1, 2. So we don't even need any contribution from the green vector. Yes.
If it would different, can you solve it like we did before? Would you like to make it like 1, 1, 1, 2, 1, and then like some vector and then what we want?
Yes, exactly. So that was my next question. And you got it exactly right. So if this was harder and we couldn't just like guess, oh, this is 1, 0, then how you solve it is it's going to be the vectors like as columns times what are these two numbers? What is going to be this number x? What is going to be this number y? And we want to set it equal to 1, 2. How you can always check that you're writing these like correctly, like where is the column going, or like where's the numbers. So over here we have, okay, we have 1, 2, 1, 1 times xy. Okay, wait, why don't I do it like this way? If I have an x and a y here. So we have 1, 2 equals x, some number, times 1, 2, plus y times 1, 2, or 1, 1. If we write it as the orange vector as the first column, 1, 1 as the second column, times x, y, and you're multiplying this, how do you multiply things? You write x plus y, 2x plus y. And if you extended this top part, what do you get? You get x times 2x plus y times y, which is x plus y to x plus y. So that's how you can check that you're writing things in the correct order. So we know that we need to set this matrix multiplication equal to our answer. Okay, so let's do an example. Oh, yes, okay. Recitation question 30. So for a vector with components x, y in our standard basis, express the same vector with components a, b. So this is our new vector in this weird basis, v1, v2. So we're given xy. They're telling us we know what the vector xy is in our regular basis. We need to find what is AB going to be. Like, what is that new thing? And specifically, our new basis is v1, v2. Or you can write it as 1, 1, 2, 1. So as we said previously, we want some combination of 1, 1 plus some multiple of 2, 1 to equal, oh wait, sorry, I should put A's and B's here, A and B to equal what we're given. And so the way you would solve this in general is write this matrix AB equals XY. So this is just very like abstract way of looking at it. Any questions on this? Yes.
What would we do to solve that?
So there's nothing to solve for this one, but if they gave you like write 1, 2, or write 5, 6, so like write 5, 6, then you could just plug in 5, 6 and solve for AB. You can solve for AB either method 1, doing an augmented matrix and solving it like that way, or you can do the x equals A inverse B version, where you multiply both sides by the inverse of your matrix. So you would be given x, y as numbers, and then this looks exactly like the AX equals B question, which we saw last week. Any other questions on this example? Okay, last topic is determinants, most fun topic. So there's two ways to calculate determinants, right? If you learned it some other way, should also be fine. The two most known ways are either I call it the cross way. I know some people use this, where they write out the 3 columns and then rewrite the first 2 columns, and they kind of like go like a crisscross way, and they multiply the purple plus the other purple plus the other purple minus the oranges. So or I like to do the minor expansion way. I find this more natural to me. But what you do is you take you always start at the top left-hand corner. You do that number times the determinant of, like, you X out that row in the column. So what you're left with is the determinant of these two terms. Then you do subtract this top middle term. And again, you like kind of think of it as Xing it out, times the determinant of what's left over. So these four terms. And then you do this term, and you can think of like canceling out those tons of rows. So this term times the determinant of what's left over. And you keep repeating this pattern over and over again if it's like a bigger matrix. Okay, and I listed some properties there for you guys, but let's do an example. Oh, wait, let me explain determinants and row reduction. So last week we learned all about row reduction, right? So row reduction is an easier way that we can find a determinant of some complicated matrix. Like we don't want to do all of the minor expansion. That's too much work, right? So instead, we learned the 3 common row reduction techniques: switching a row, rescaling, and then combining 2 rows. So when you're switching the rows, it multiplies the determinant by -1. When you rescale a row, it multiplies the determinant by whatever you multiply the row by. So I put a constant C. If you're combining rows, then it doesn't change anything with the determinant. So if you start with some matrix A and you go to your row reduced, much easier matrix to find the determinant, most likely it's going to be a diagonal matrix or upper triangular matrix. Then the determinant of A is going to be the determinant of this easier matrix to calculate, divided by all the operations that you just did in green. Oh, okay. So for example, if we have A equals this matrix here, I'm going to row reduce by, I don't want this 1 here. So I do R3 minus R1, which gives you 0. 4 minus 2 is 2. 6 minus 3 is 3. Then I don't want this 2 here anymore. I want it to be upper triangular, which is the easier way. So I do R3 is R3 minus 2 times R2. So 2 minus 2 is 0. 3 minus 4 is -1. Now we know what the determinant of this is, right? Does someone want to shout it out? Yes. So the determinant of R is -1. What were the row operations we did? Well, we did a combining thing. So multiply the determinant by 1, no change. We did another combining thing. So multiplied by 1, no change. So the determinant of our A, our original matrix, is -1 over, there's no changes, so it's still -1. Any questions on this? Yes.
So when you roll with a bigger matrix,
Mhm.
the easiest way to find it is to like do row reduction.
Yes. Yes. Because if you had a huge matrix, like even in this case, a 3 by 3, like to do minor expansion, this would be 1 times the determinant of this, minus 2 times the determinant of this, etc. And then you have to keep writing it out. So even in this case, row reducing makes it easier. Yep. Yeah, Celia.
Are there any cases where row reducing would make it more difficult?
Well, if you just have a 2 by 2 matrix, don't row reduce. But yeah, I think row reducing usually is easier. Okay, let's do an example. So again, thinking abstractly, just so that, like, thinking about things. So if the determinant of A, B, C, this thing equals 3, what is the determinant of this matrix? So you want to do some row operations and figure out what could this determinant be. So I'll give you guys a couple, like, minute or so to think about this or figure it out. Oh, before I forget to mention, I did change this week's office hours to like the night one on Wednesday. I'm changing it to 12:40 to 1:40 on Zoom. But I still have office hours today, like after this recitation, in here or Zoom also. Yes, PM, not midnight. I think Richard is the only one who will stay up till midnight. Okay, does anyone want to come up on the board and write their answer? Any volunteers? Or do like one step. How about we write?
Yeah.
A, B, C. Someone volunteer to do the first step. Like, what should I row reduce? What should I do?
Okay. So I get A, B, C, R, S, T, X, Y.
Okay, what should I do next? 1 and 3.
Oh, 1 and 3. Okay. So I have X, Y, Z, R, S, T, A, B, C.
Okay, next. Yes.
You can multiply row 3 by 3. Okay. 3 becomes 3 times R3. So we have X, Y, Z, R, S, T, A, 3, B, 3. Okay, next up. Yep. Okay, row 3 is row 3 minus row 1. So we have X, Y, Z, T, minus X, 3B minus Y, 3C minus D.
Okay, final step.
Yes,
Rescale row 2 by -2.
yes. R2 equals -2 times R2. X, Y, Z, 2R, 2S, 2T, 3 minus X, 3B minus 1.
Sorry. Thanks. Yes. Mhm. Like, so like you did the determinant of like the bottom thing and like the minor expansion, like x times the determinant of.
My first step was to combine row 1 and row 2. Like I went back.
Oh, okay. Yeah, it doesn't matter like how many steps you take, as long as you know what row operations you're doing to get to this final thing.
So it doesn't matter which one I start with. Like I started with the good and the bottom one, like not the one like the one without it.
Oh, I see. So you did like starting from the bottom thing, and then you did like
Yeah.
yeah, I think it still works. Okay, so we did all of this. This is our row reduced version. This is our not reduced version. So we'll call this like A. Okay, so we did a switching. Switching multiplies by -1. Switching multiplies by -1 again. Scaling by 3 multiplies it by 3. Combining doesn't do anything, so it's just a 1. Scaling by -2 multiplies it by -2. So by our formula, determinant of A equals determinant of R over RU, right? And we're trying to find what is R. So determinant of A times all our row operations U equals determinant of R what is the determinant of A? We said it's 3. What were all the row operations we did? We have a -1, a 3, a 1, and a -2. Determinant of R, which is times negative. So the determinant of R equals -18. Any questions on this example? Yes.
So any sort of rescaling at all, like results in one. So if you like did not like for example, if you did like R3 equals R3 minus 2 times R1, it would still be 1.
Yes.
Okay.
Any other questions on this? Okay, should we, okay, I think you guys can do that one. Okay, does anyone, yeah. Yeah, okay, let's do general question.
It's like triangle.
Oh, let me see. Oh, this?
Yeah, you just like do it as you would for parallelogram.
What is the area of the triangle with vertices? Yes. Yeah, because or volume of a triangle is half base height usually, but base height is like our area. And how do you find area of a parallelogram? Just the normal way, divide by 2. Okay, yeah, I'll open it up to general questions now, unless you want to do more of my prepared questions. It's up to you guys. Yeah. Yes.
So as we like it's here to like determine A to determine R over B. Which one's like R A? How do we know when to like divide or split?
So A is the original matrix they give you. R is the reduced version. So like here, it's not in the reduced version, but usually you would reduce it to an upper triangular form. So R is like whatever you reduce it to. And A is the usually, okay. In this example here, it was kind of like backwards thinking-ish, but usually A is whatever matrix you start with, R is what happens when you finally reduce it.
Okay, so here we're saying that like the reason why we multiplied in this case is because we started with the reduced matrix.
You can think of it as the reduced matrix, but this is just the matrix we're starting with, which is A. So wait, someone talked about doing it the other way. If you did it the other way, so like this complicated thing is A, I guess. Like, okay, I don't want to like do it all out, but you can also think of this as A and this as R. You're just gonna get different like operations. Like instead of multiplying by 3, you might multiply by 1/3 instead.
Okay.
So yeah, I like to think of it as whatever matrix you're starting with is A. You do a bunch of row operations, whatever you end with is R. Yes. If you want to try it the opposite way to like understand it better, you can try and see if you get the same answer. Okay. Other questions? Yeah. Yes. Prep quiz. Practice. Okay. 14. Yeah. Okay. I was going to do this one. Okay. For which values of scalars A and B is the triple scalar product always 0? So last week we learned how to do it like the long way, I guess. You do the cross product first and then dot product it. This week we learned there's an easier way. You could just do the determinant of U, V, W. You write each vector as a column. So here, let's to like visualize it more. Let U, oh sorry, let V equal, I don't know, J, K, L, W equals F, G, H, right? So we want to find the determinant of, this is A times B plus B times W. So I'm just going to multiply A times each component in B plus B times the component in W. So we get AK plus BG, AL plus BH. That's our first column. The next column, we put the V, right? V is JKL. Last column, we put W. W is FGH. So we want to find the determinant of this. So I'm going to call this matrix A. Like we started with A, now we want to row reduce, get to R. So let's row reduce it. If we do, oh, I see why you, let me think. Okay, so you can do column operations also, but that might get kind of confusing. So let me write it. Okay, I said you usually write the vectors like downwards. It doesn't matter. You can also write the vectors horizontally. Let me write them horizontally so that it's not as confusing. Okay, because yeah. And we can write them horizontally because the determinant of A equals the determinant of its transpose. So it doesn't matter if you write them vertically or horizontally. Let's write them horizontally. Now let's do row operations. So we have, let's do row 1 minus A times row 2. What do we get? We get AJ plus BF minus AJ. Those AJs cancel out. Then we get AK plus BG minus A times that second column. These cancel out. And the same with this last column, AB plus this minus AL. These two cancel out. JKL, FGH. Okay, then let's do row 1 minus B times row 3. We get BF minus BF, BG minus BG, BH minus BH, JKL, FGH. What does this give you? This is 0, 0, 0. You have a row of all zeros. So the determinant, no matter what, even if you do minor expansion, you'd be doing 0 times determinant of this. But that doesn't matter, it's still 0. Minus 0 times this, plus 0 times this. So this determinant is always 0. So the answer is that for any A and B, the triple scalar product is 0. No matter what. It doesn't matter what numbers you put in here. You notice that we row reduce and we always row of zeros. Any questions on this? All right, recitation's over. Yeah, I've off hours now.